So there are a couple of things that we haven't done, and source transformation that we also wanted to look at and see if this is the same thing as we do for the resistive circuits. So for the source transformation, let's look at the example here. Our objective of this problem is to find the voltage across the 2 ohm resistor on the far right, but we wish to use source transformation. If we recall, source transformation is to converting the voltage source into current source. And we notice here we have this one, that voltage source in series with something, element. We can definitely convert that into current source. Then in parallel with that exactly the same element here. So this time we can just go ahead and do that. So this is how we make a transition. Now the source, the current source, the IS here, I, is equal to the voltage divided by that element's impedance, which is negative J1. But you can see when we do that here, the good thing, the advantage of that is that you can see now we can couple with the 1 ohm resistor. And so we can combine this and do a further simplification. Now once we do that here, we also notice, let's keep on going, we notice here, this actually is in parallel with a current source. So this current source and this current source, they are in parallel, and they can also be combined. Now eventually, this is going to be, I'm just pointing out the direction, how to think about the problem here. Eventually this is going to be just one current source, whether going up or going down depends on the final result here. And in parallel with the combination of this. So I'm going to call this Z1. So this is just a Z1, whenever that is. And notice here, we're up to here at this point now. So this actually is the negative here, positive here, that's the voltage source. And that's basically is what we're going to stop right here. You can see once again, we can convert that into a voltage source in series with that element Z1. Now you can see now we change the position of the 2 sources. We can actually add these 2 sources together to simplify it further. This is the advantage of using source transformation. So let's go do that. Let's start with that one at a time. So the first thing we have here, the current source is equal to the I, let's call this I1, is equal to the voltage source, which is 12, divided by negative J1. And that gives us 12, so this is 12. -90°. So this is I1. Notice the polarity here. Element. This is 70. In series, in parallel with, we would want to simplify negative J1. In first thing we did, and we called this I1 with the equivalent, and we're going to combine this, that's 1 ohm, and also into the second current source that's going down, and which is 2 amps. Current source, we have resist capacitor right here. So the combination of this will be, then we have inductor here. The summation of the two current sources, our objective. What is VO? Just one element here, which is a combination of the resistor and capacitor. We're going to call this Z1. And this current source here, I'm going to call this I prime, where you can see clearly the I prime is equal to I1 minus the second one here, because I'm using the same polarity as I1. So that's minus the second current source, that minus 2, which you can see this is 12J minus 2. That's I prime. Now if we combine this, make it to a phasor expression, that will be 2 squared plus 12 squared and take square root. We figured out that's to be 12.66, and the phase angle is equal to the inverse of tangent of that 12 divided by negative 2. We end up with 99.46 ampere. Now let's look at what's Z prime, the Z1. Z1 is equal to, remember that is 1 of 1 plus 1 of negative J1, then the whole thing need to be take it over, reciprocal once again. So that ends up to be, that's 1 over 1 plus 1 over negative J1, and take reverse. That turns out to be that negative J1 times 1, and then 1 plus negative J1. So by doing that computation, the numerator is simply just equal to negative 90 degrees, because that's just J, negative J. And denominator is root 2, negative 45 degrees. So that is quite straightforward. That gives us root 2 over 2, and the phase angle is negative 45 degrees ohms. So as we talked about earlier, once we have that combined up to that point here, there's A prime up to A prime and B prime. And what we can do then is that we once again convert that back into voltage source. So we wanted to convert that back into voltage source because we wanted to combine with this second voltage source there. So this is our Z1. And that voltage source here, V2, let's call V1. We haven't used V1 yet. And this is this voltage source we wanted to combine. Negative. That's a 6 volts. So, V1. V1 is equal to I prime times Z1. So that is equal to root 2 over 2 negative 45 degrees as a phase angle, and multiply by Z1, and that's a Z1 multiplied by current. That current here is equal to 12.66, and the phase angle here is 99.46. So for the multiplication, the phasors, that's also straightforward, that we have the magnitude. We have the magnitude here, multiply the magnitude here. And that gives us 12.166. Then the phase angle is simply just this phase angle plus that phase angle. So that gives us, oops, the multiplication of square root of 2 divided by 2 and multiplied by 12.66, that's actually give us 8.6. And the phase angle of negative 45 plus 99.46 gives us 54.46 volts. So now finally you can see we're going to put the load resistor back into the circuit here. And the load resistor is 2 ohm resistor right here. And this is the V0 we wanted to figure out. So you can see now we're simplified everything. V0 simply just equal to the current going through the 2 ohm resistor multiplied by the 2 ohm resistor. And the current going through the entire current here is just equal to the total voltage here is V1 plus 6 divided by the Z1 multiplied by 2. So you probably recognize that just by VDT, right? Just by VDT. So VDT is equal to the impedance of the resistor, which is 2, divided by 2 plus Z1, and multiply by the total voltage, and the total voltage here is just equal to V1 plus 6. Now the current is, the total current is the total voltage divided by the total impedance, which actually is Z plus 2. And that comes out the same thing as the VDT. So what we need to do is we just need to put the values in. So the V0 here is equal to 2 divided by 2 plus Z1, and the Z1 is equal to root 2 over 2, and phase angle is negative 45 degrees. Then multiply by the total voltage here is the V1 plus 6, which is 8.6. Phase angle is 54.46 and plus 6. So now you can see what we need to do is you can see we are dealing with a phasor plus real number. So we have to convert that into a rectangular coordinate And the real number is 8.6 times cosine 54.46, that's the real part. And the imaginary part here is j 8.6 times sine 54.46. So we need to be very familiar with the conversion back and forth. And so we are also facing the same thing here. This is a real number, and this one here is a phasor expression. And so we need to, again, convert that into rectangular expression. So now let's finish that up. And we're going to plot 6 here, the whole thing here. That gives us 13.03. And the phase angle is 32.47. And now if we go back to this part here, and then multiply by this, we end up with 10.23, and the phase angle is 43.78 degrees. Volts. This is our V naught. Again, let's go back and review in summary of this source transformation. You can see the idea is really simple. If we had a resistive circuits, that's in a couple of minutes, we can finish everything up. But this problem takes us for a while because each step of operation involves the phasor operation. So this is the only thing that we really need to be careful.